Hello everyone, my name is Geeta. I am a PhD candidate at the Technical University of Munich and I worked on this paper along with Professor Meyer and Professor Jakobsen. The title of our paper is Why Do My Blockchain Transactions Fail? A Study of Hyperledger Fabric. The concept of distributed trust and immutable ledgers was reintroduced with the launch of Bitcoin back in 2009. It became even more popular when Ethereum was launched. Such blockchains are now known as permissionless blockchains because they allow an unlimited number of unauthorized participants. Also, they can guarantee only a limited throughput. Due to these reasons, enterprises were hesitant to adopt such an open platform, and therefore the idea of a permissioned blockchain came into existence, with systems such as Quorum, Corda, Hyperledger Fabric, multi-chain, etc. Such systems allow a limited number of authorized users and can also guarantee a much higher throughput. Our focus today is on Hyperledger Fabric because it's one of the most widely used blockchains both in research as well as in the industry. Hyperledger Fabric has a design that uses a replicated world state distributed across a set of peers. Also, the transaction flow in Hyperledger Fabric follows an optimistic concurrency control model. Due to these reasons, various concurrency-related failures can occur, like MVCC read conflicts. And in our experiments, we observed that more than 40% of the total transactions failed due to concurrency-related failures. So the main motivation for our work is the lack of an extensive study of such failures in the literature. Also, Fabric provides various configuration parameters, and each of these parameters have a significant effect on failures. For example, a simple change in the block size could reduce the failures up to 60%. Further, various optimization strategies are available in the literature that try to improve the performance of Fabric by various strategies such as transaction reordering, for example. But there's a lack of a fair comparison between these different strategies. Therefore, we felt that there's a need for useful recommendations on how best to choose the different parameters as well as the different optimization strategies. So our contributions in this paper include a formal definition of all the different concurrency-related failures in Fabric, evaluation of the different configuration parameters and the effect of these parameters on failures. Further, we compare the three optimization strategies of Fabric on a uniform configuration setting. Also, we developed an automated test bed integrated with a benchmarking system for all our experiments. Finally, we provide a set of best practices for users on how to choose the different configuration parameters and decide on optimization strategies. So, first, a short introduction to the transaction flow in Fabric. Fabric follows a execute, order, validate model, where in the execution phase, the clients interact with the peers. Some of the peers are assigned as endorsers based on an endorsement policy, which says exactly how many peers need to sign or endorse a transaction. So based on the policy, the client sends a transaction proposal to the endorsers. The endorsers execute the smart contract, which is called a chain code in Fabric, and also verify the client signatures. The execution of the smart contract or the chain code generates a read-write set, which is a set of all the read and write keys of the transaction. The proposal response is sent with the read-write set along with the peer's signature back to the client. Next, the ordering phase. Here, the clients send the read-write sets from the endorsing peers and their signatures to the ordering service. The ordering service is a set of one or more nodes that follow a crash fault tolerant consensus model and orders the transactions into blocks. These blocks are cut based on either the size of the transactions, the length, the number of transactions, or a block timeout. The validation phase begins when the ordering service sends these blocks of transactions to the different peers, to all the peers in the network. The peers in turn validate these transactions. Validation includes validating the endorsing peer signatures as well as the read-write sets. So the read-write sets from the different endorsing peers are compared with each other and also with the current world state. If both these validation passes, then the database or the world state is updated. Also, the entire block of transactions is then appended to the ledger. So this is the execution ordering validation model that Fabric follows. Due to this model, various transaction failures can occur. These are the three types of concurrency-related transaction failures in Fabric. I will go through an example for each of them. So the first one is the endorsement policy failures. So this occurs when inconsistent world states happen. So here peer 1 and peer 2 have a different version of the key A. This occurs maybe due to network delays or if peer 1 is lower than peer 2. When such inconsistent states occur and a client sends a transaction, for example, read A, to both the endorsers, the read-write set generated by the endorsers would have a version mismatch, and in the validation phase, this transaction will fail. This is the endorsement policy failures. The second type is the MVCC read failures. Here, let's again consider the key A with a consistent world state between two peers, and in the validation phase, a block of transactions, of two transactions are coming in. Transaction 1 is writing to the key A. When the write A is validated, the database gets updated to a new version. Thereby, the next transaction which reads A has a version mismatch, and therefore this transaction fails. Such dependencies between transactions can occur within a block or across blocks, and thereby they're called intra-block or inter-block MVCC read conflicts. The third type of transaction failures is the phantom read conflicts. So Fabric identifies this as a separate conflict, but essentially is an MVCC read conflict for range reads. For example, if a range of keys from A to Z are being validated, and if at least one of them has a mismatch with a world state, then the entire transaction fails. So the endorsement policy failures are caused due to inconsistent world states, and this can depend on various configuration parameters such as the number of peers across which the world state is distributed or the latency of the entire transaction flow. For the MVCC read conflicts and the phantom read conflicts, this is caused due to transaction dependencies. So again, other configuration parameters such as the block size, which splits the transactions across blocks or includes it into the same block, will affect such failures. Therefore, the study of the different configuration parameters is important. So our experimental setup begins with the Hyperledger lab, which is our automated testbed that can deploy a Kubernetes cluster and the Fabric network. We integrated this with a Caliper benchmarking system, which is a popular benchmarking system for different blockchains. We also further developed 4 chain codes based on popular use cases from the literature: electronic health records, digital voting, supply chain management, and digital rights management. We also have a generator for controlled experiments, which can generate a synthetic chain code at a workload. In total, we conducted 970 experiments with 11 different configuration parameters and measured 5 metrics, which are latency, throughput, and the 3 different failures. So here I'll show a few of the results from our paper. The first set is regarding the effect of the different configuration parameters. In these 3 graphs, we measure the best block size, which is the block size at which the transaction failures are the least, and different transaction arrival rates for 3 different chain codes. We can see that the best block size has a high correlation with the transaction arrival rate as well as different chain codes. Therefore, block size and failures have a high correlation. If you look at the exact value of the number of failures in these three chain codes, we can see that a simple change in block size can even reduce the failures up to 60%. Therefore, our recommendation from this experiment is to adapt the block size dynamically based on the incoming workload and not fix a static block size. The next parameter that we considered are the organizations and the endorsement policies. Every peer or client in the network are members of an organization, and a group of organizations make up the fabric network. Usually, the number of organizations are set based on the actual physical organizations in an enterprise. The endorsement policy, as I said before, specifies the number of peers that need to endorse a transaction. So we can design the endorsement policy in different ways, and we have shown four different definitions of endorsement policies here. P0 and P3 require n signatures or a quorum of signatures. P1 and P2 require only two signatures, but the organization from which these two signatures are to be obtained are different. P2 has more sub-policies, which specifies exactly which organizations need to provide each of the two signatures. Our experiments show that with the increase in number of organizations, the endorsement policy failures also increase. This is because when the number of organizations increase, of course the number of peers also increase, and therefore the world state has to remain consistent across more number of peers. With endorsement policies, we see that when more number of signatures are required, the endorsement policy failures increase. Again, the same logic that when more number of peers need to have consistent world states, the failures will increase. Even with the same number of signatures are required, we see an increase with the increase in sub-policies. This is because the entire endorsement policy is passed during the validation phase, and each sub-policy is considered as a separate search space. This increases the latency of the entire transaction flow, thereby increasing the probability of consistent world states. Therefore, the endorsement policy failures are related to how you design the fabric network. So our recommendation is to simplify this fabric design. For example, the number of organizations need not map to the actual physical organizations in an enterprise. Instead, organizations performing the same functionality or in the same locality could be clubbed together. Similarly, for the endorsement policy, every organization need not be a part of this policy. Only the stakeholders need to be included in the policy. The next experiment shows the transaction failures, the total transaction failures with different workloads with a synthetic chain code. And we can see that the update heavy workload has the most number of failures. Therefore, the failures depend on the transaction dependencies. Updates, of course, have more transaction dependencies. So our recommendation here is to optimize the chain code such that these dependencies are minimized. For example, you could consider using delta updates. Here, if a key is being updated with a simple increment or a decrement, you could consider writing the increment operation to different delta versions of the key and only aggregating them when the value of the key is required. This way you could change an update heavy workload to an insert heavy workload. A second example would be to convert range queries to reads. For example, if you're reading a range of keys to evaluate the total or an average, you could consider having a separate key that stores the value of the total or average. This could convert the range query to a simple read. Of course, such optimizations are totally dependent on the kind of workload and the specific use case of your chain code. The second recommendation we have here is to batch read transactions. This is because there are certain situations where the reads or even range reads are used only for debugging, logging, or auditing purposes. In such cases, we could consider batching them and only executing them at a specific time interval in the day. The next set of experiments are based on the different fabric optimizations. First, we consider Fabric++. Fabric++ generates transaction dependency graphs or conflict graphs per block, and they either reorder the transaction or early aborts the transaction to remove these transaction dependencies. A simple example is shown here where a reordering of a read and write could avoid a transaction conflict. Thereby, they resolve intra-block MVCC read conflicts. Our experiment with Fabric++ shows that it is effective in reducing the failures in most cases. But an exception is when there are a large number of large range reads, for example, up to 1,000 keys are being read in the digital voting and the supply chain management cheat codes. Such large range reads would have dependencies with multiple transactions, and therefore reordering will not be very effective. But if the range is smaller with 8 keys, we can see that Fabric++ is effective. So our recommendation is to avoid such large range queries or convert them, as I mentioned in the previous slide. Second exception we see is where the reordering possibilities are very less, for example, with a very read-heavy workload or a delete-heavy workload, where the reordering algorithm has to execute, thereby increasing the latency, but the result may not resolve conflicts. Therefore, here our recommendation is to evaluate the reordering possibilities before using reordering strategies. The second optimization strategy is stream chain. Here the transactions are sent one by one without creating blocks. Therefore, the time required for block creation is reduced. Also, they store the ledger and the world state on a RAM disk, further reducing the latency. And we see that this reduction in latency reduces failures significantly. But we observe that at higher transaction arrival rates, due to the one-by-one streaming, the throughput decreases. So our recommendation with stream chain is to use it when we expect a low workload. The third strategy is Fabric Sharp, which again similar to Fabric++ generates transaction dependency graphs and reorders the transaction. But here the graphs are generated across blocks so they can resolve both inter and intra-block failures. We see that Fabric Sharp is very effective in reducing all the MVCC read conflicts, and the only failures that remain are the endorsement policy failures, which is shown in the second graph. Further, Fabric Sharp does not support range queries, so they cannot resolve phantom read conflicts. So endorsement policy failures and phantom read conflicts are not considered by Fabric Sharp. So our recommendation is to use Fabric Sharp when we do not require range queries or convert range queries to reads. So based on our experiments, we also point out some future research directions that could improve the performance of Fabric. One is an adaptive blockchain system that can adapt the block size based on the incoming workload at the time of chain code. The second research direction would be to explore endorsement policy failures because none of the optimization strategies discuss this type of failure. So there are different research optimizations in the literature that focus on inconsistent world states, and such research could be integrated with Fabric. Our third research direction is to optimize the chain code. So I pointed out two examples of how the chain code can be optimized, and a fruitful research into this direction would be useful. So in conclusion, we point out that the ideal configuration settings can affect transaction failures. The effect of the different optimization strategies depend on the type of workload that is used. Further, our general recommendation is to extensively analyze the expected workload or even simulate the expected workload and study the type of failures before making design decisions. The testbed that we have developed is available as open source for further research. You can see the testbed at our GitHub link, and also an extended version of the paper is available in arXiv, where we have provided more results and larger graph renderings. Thank you for your time and attention.